Thank you. So I'm Josh Renner. I'll be telling you about my thesis research, which is in progress on high-pressure xenon detectors, with the main focus on searches for rare physics. And this is our high-pressure Xenon TPC time projection chamber at Berkeley Lab, which I will be telling you about during the talk. But first of all, so what do I mean by rare physics? So that is a physical process that, if it exists, is extremely difficult to detect. So two examples that I'm going to focus on are neutrinoless double beta decay and the interactions of WIMP dark matter. So in each case, we have some energy deposition by the process in a detector volume, and the detector's job is to determine that amount of energy to observe the process. So how do we do that with a gas-based detector? So in general, a gas-based detector, the action happens in the pressure vessel, which is full of gas, and an interacting particle will deposit its energy in the gas, producing ionization and scintillation. And so there are several other systems used in support of the pressure vessel. There are often gauges and monitors and computers to acquire and analyze the signals from the detector. And there's also the gas system, which is used to fill the detector with gas, remove the gas from the detector, and also purify the gas to greatly improve the detector's performance. So the main goal here is to detect ionization and scintillation deposited by particles. How does that happen in a gas-based detector? The incoming particle deposits its energy and produces ionization by knocking electrons out of the atoms in the detector medium. So some number of electrons are produced, and they're drifted using an electric field to some amplification region in which each electron is amplified into more electrons, or somehow the signal is increased so that it is measurable. So in this case, we don't actually use this in our LBL TPC, but this is an example of a large electron multiplier, which is two copper plates with a dielectric sandwiched in between them, and holes drilled into those plates. So the electron essentially moves into this hole with high electric field and is accelerated, ionizes more electrons from the gas, and comes out in an avalanche, producing a larger signal. So that's an important step in the detection process. And then, of course, that amplified signal is read out. And so one possible way of doing that would be measuring the amount of charge induced on some electrode. And from the measurement of that charge, one can determine the energy of the event. So the number of electrons produced by the ionizing particle determines the energy of the particle. That's in general how a gaseous detector works. Also, the incoming particle will produce scintillation during its initial interaction, and that can be read out and amplified by devices such as photomultiplier tubes. So ionization and scintillation in gaseous detectors, and those are measured to determine the energy of a particle. So now I'm going to talk about neutrinoless double beta decay, which is a process that we're interested in. And first of all, single nuclear beta decay involves the decay of a nucleus in which a neutron becomes a proton, an electron, and an antineutrino. This is called beta minus decay. There's also an analogous beta plus decay. So this neutrino carries off some of the energy of the decay, and it was in fact this process that led to the proposition of the existence of the neutrino in 1930 by Pauli, same physicist behind the Pauli exclusion principle. So they had noticed that that all of the energy should be in this electron, ignoring the recoil energy of the nucleus. And so the electron should have some fixed energy, but it was being carried away by this mysterious particle, the neutrino. So it turns out that this can happen twice simultaneously if you have a nucleus such as Xenon 136, in which a single beta decay would not be energetically allowed, but a double beta decay would decay to a nucleus of lower energy and would be energetically allowed. So in these cases of double beta decay which have been observed, we've only ever seen the double beta with two neutrinos. So this happening two times, getting two neutrinos. However, if the neutrino were its own antiparticle, it's been proposed that the decay could occur with zero neutrinos. So one of or both of those neutrinos effectively annihilate each other and disappear, and all of the energy is observed in the 2 electrons of the double beta decay. In that case, the neutrino would be called a Majorana neutrino. So one of the major questions about neutrinos is a neutrino Majorana, and that can be addressed by observing or attempting to observe neutrinoless double beta decay. So what is the neutrino? In general, it's a small neutral particle, and it exists in 3 different flavors, and there are 3 different neutrino masses. However, those 3 flavors do not correspond one-to-one with the neutrino masses. In fact, each type, which is associated with a charged lepton, for example, an electron, each flavor type is actually a quantum mechanical superposition of mass states. So the 3 mass states have some combination of flavor states, and a neutrino interacts in a state of flavor. So when a neutrino initially interacts, it could be later observed in a state of a different flavor as a neutrino oscillation, and that led to the discovery that the neutrinos actually had mass. They wouldn't be able to do that if they didn't have mass. Unfortunately, we've not yet been able to determine the absolute value of this minimum neutrino mass, only differences in mass between the neutrinos, and in fact, we're missing a sign in that picture also, so we don't know whether we have 2 light neutrinos and 1 heavier one, or 1 light neutrino and 2 heavier ones. So those are questions that can be addressed at least partially by a neutrinoless double beta decay. And so how can it do that? The actual rate of the decay is dependent on 2 factors which depend on the nucleus, the candidate nucleus, and another factor which depends on some combination of these mixing parameters that determine how the flavor and mass eigenstates mix, and the neutrino masses themselves. So not only would a non-zero neutrinoless double beta decay rate tell us that a neutrino is its own antiparticle, it would provide some information through this m double beta of the absolute scale of the neutrino mass, and it would do so as follows. If one chooses different combinations of the measured neutrino mixing parameters and the allowed possibilities of minimum neutrino mass versus the effective double beta mass, one gets this sort of plot in the different cases of where the neutrino mass hierarchy is normal, so 2 light neutrinos and 1 heavy neutrino, or inverted. And so neutrinoless double beta decay measures this axis, essentially. We'll measure some value, and therefore if we were able to get below the inverted hierarchy, we've essentially ruled out that possibility. And so this is the current limit in Xenon on neutrinoless double beta decay, and the future generation experiments are expected to initially at least get below this inverted hierarchy. So we can also rely on information from cosmology to produce a limit on the sum of the neutrino masses, which further constrains this plot. So and it's been generated in a Monte Carlo fashion so that the more density of points represents a higher number of combinations of neutrino mixing parameters that allow for these specific values. So we can rule out a lot of the parameter space using neutrinoless double beta and cosmology measurements. So all of this is an effort to learn about the neutrino. So in detecting neutrinoless double beta, we have to meet several conditions, which we believe the Xenon can meet. Good energy resolution, having a significant amount of mass, and low background. So energy resolution is determining that energy of deposition very precisely. And so what one would expect to see in a neutrinoless double beta experiment is a spectrum of energies due to 2 neutrino double beta, and then a small peak at the end due to 0 neutrino double beta if it does exist. And in order to separate those 2 peaks, one needs to measure the energy very precisely. And so Xenon is a good candidate for being able to do that, which I will explain. One also must have a large amount of mass. And so these are some proposed and operating and in development neutrinoless double beta experiments. Many of them have hundreds of kilograms to tons of proposed mass of the isotope of interest. And we also want low background, and this is also the case for dark matter searches. Many of these underground laboratories provide kilometers of equivalent water vertical depth, and that is used to reject background from cosmic rays. So that's also important. So what have we done at LBL towards this effort with high-pressure xenon? So this is our high-pressure xenon TPC. TPC is time projection chamber. That is a type of detector, and I will explain how that operates. This is our pressure vessel. Here's our gas recirculation and purification system. And then these are where the signals are read out into other computers, which are over here, to do the acquisition and analysis. The different parts of the detector are separated by these wire mesh grids to which high voltage can be applied and produce drift fields of different magnitudes in different parts of the pressure vessel filled with xenon. And these are our photomultiplier tubes, which are at this end in the back here of the pressure vessel, and they observe light produced during the interactions of the particles in the xenon gas. In fact, we're only reading out light, so the ionization and scintillation are both observed as light in this detector. So inside, we have a drift region where the particles interact, and the ionization is drifted to an electroluminescent region, which I'll explain in a moment here, that produces that converts the ionization to light, which are then read out by photomultiplier tubes. And the size of the vessel is about 10 liters in total, so it fits about on the order of a kilogram of xenon gas inside of it, and we operate at about 10 to 15 times atmospheric pressure. So here's a diagram of what I've just shown, and the detection process occurs with the particle depositing energy, producing ionization and scintillation. Scintillation is initially detected, and the ionization is drifted over here to this narrow region where it's accelerated fast enough to make more xenon light. It excites xenon atoms, causing them to emit light. And that light is detected also by the photomultiplier tubes. And so both the ionization and scintillation are observed as light, and we get a signal like this. So initially, when the particle interacts, we get an S1 signal. That's the initial primary scintillation. Then there's some downtime where that particle is drifting. It's about 80 to 100 microseconds. And then we have a large S2 signal where all of that light is produced by the electroluminescence process. And this is the amplification stage that I was explaining earlier. And with electroluminescence, that you have an advantage of having very low fluctuations on the amplification, so very precise measurement of the energy. So when we place a gamma ray source next to the TPC, and we integrate the values of these S2 charges, so that tells you how much energy. Remember, the measurement of the charge or of the ionization gives you the energy of the event. We get this spectrum. So we see xenon X-rays, which can be produced by the interactions of gamma rays and xenon. We also see these events which did not fully deposit all of their energy. The gamma scattered out of the TPC but left some of their energy, Compton scatters, and then the full energy peak where we got all of the energy of the cesium gamma, which is at about 662 keV. So another detail about the detector is that due to the geometry of the pressure vessel and the detector itself inside, the amount of energy observed tends to decrease for a fixed input energy value as the radial distance from some central part of from central axis of the detector increases. So if we make a cut here, we can get better energy resolution just by looking at a smaller area of the detector. So with this cut, we've been able to achieve a Gaussian peak of about 1% full width half maximum of the mean energy value in energy resolution. And so if we extrapolate what we would expect for an energy deposition at the double beta decay energy value that we are attempting to detect, that small peak at the end of the spectrum, we would anticipate about 0.5% energy resolution. And so that should be very good and should be a big advantage in a double beta decay experiment to have such good energy resolution. We've also attempted to place a small array or an array of 64 silicon photomultipliers, which also convert light into electrical current like PMTs, and we've observed a muon track. This is positioned right next to that amplification region, so the light hits the detectors without having traveled so far, so we can get good position resolution. We've reconstructed a muon track here, so we haven't been taking much tracking data recently. This was an attempt to develop the tracking concept of the NEXT experiment. So NEXT, these are some. So this is from Spain, the Canfranc underground lab where NEXT is planned to. The large NEXT detector is planned to be based. It has many more photomultipliers and silicon photomultipliers for tracking and energy measurements. It operates similar to our prototype and another prototype which is developed in Valencia, Spain, and we're anticipating up to 150 kilograms of xenon enriched to the candidate nucleus of interest to be placed inside the detector to look for neutrinoless double beta. The detector looks similar to the prototype. It has a drift region. It has an amplification region. It has the PMTs here and the silicon photomultipliers placed next to the amplification region as in the prototype. So, so that's essentially the effort at LBL towards this next experiment. And so now I'm going to move into talking about the dark matter side of our research at LBL, which started more recently. And so first, a bit about dark matter. You may have seen these pictures before. Why do we believe that there's something out there called dark matter? One of the pieces of evidence is when the rotational, the distribution of rotational velocities versus the radius from the center of a galaxy are measured, the velocities of the mass in the galaxy, the result is somewhat constant with increasing radius, and that's not expected for a disk-shaped galaxy. And in order to compensate for that effect, one can introduce a halo of dark matter and to match the observed values. So that's one piece of evidence. Another is this picture called the bullet cluster, in which two galaxies are colliding, and the X-rays, or the X-ray measurements made on this collision, which indicate where the baryonic or ordinary matter is, give a very different mass distribution than a gravitational or lensing analysis. So the stuff that is interacting gravitationally, it looks, the distribution of matter looks different than what we would expect the ordinary matter to be. So, and not only that, but these two clusters collided, and most of the matter appears to have passed right through during the collision, interacting very little. So that is strong evidence that perhaps the majority of the matter in these galaxies is some dark matter that does not interact strongly. So there's several candidates for dark matter, but the one that we're most interested in from the standpoint of xenon is the weakly interacting massive particles. So the particles interact via weak interactions, and no matter what dark matter is, the current picture of the universe predicts that, you can't really read that, about 26% of the universe is cold. The energy in the universe is made up of cold dark matter. So most of the matter out there is cold dark matter. So we're interested in figuring out just what that is. There's several ways of going about this, producing it in something like the LHC, looking up into space and detecting the gamma and neutrino fluxes, and studying how those would be different if we assume the dark matter is annihilating in space and the products of those annihilations are reaching Earth. But most importantly, for the purposes of this talk, the direct detection method, in which we have a large detector just like a neutrinoless double beta, and we're waiting for a WIMP dark matter particle to collide with the xenon nucleus and deposit energy in the detector, which is then detected in the form of scintillation and ionization. So that rate would depend on the mass of the dark matter particle and the cross section of that interaction. So we can answer questions like exactly how much dark matter is there around us. Also, it's predicted that the dark matter, because of the way the sun is moving through the galaxy, and because of the way the Earth is rotating around the sun, and because of the way the Earth rotates around its axis, we should be moving through this cloud of dark matter. And so it would look like it's coming from the constellation Cygnus. And we should be able to see, if we're looking at these dark matter events, we should be able to see a preferred direction. And so an idea from the PI in our group is that perhaps if we can look at the tracks relative to the direction of an electric field, of our drift electric field in our chamber, and if the track is made parallel to the electric field, each electron will see many ions, and there's a chance that it will be captured by these ions, recombine, and produce more scintillation light. That's less likely to happen if the track is perpendicular to the electric field, and so understanding the response of xenon to nuclear recoils, which is what we would expect for a dark matter interaction, is important to quantifying whether this will work. So in liquid xenon, they've done studies of nuclear recoils in the detector medium, in the liquid xenon, and they found that the ratio of those S1 and S2 signals are different for neutron or for elastic recoils produced by neutrons than for recoils produced by gamma rays, the ones that we've been looking at up till now that I've been explaining. So we've attempted several similar measurements in 14-bar gaseous xenon, and we should expect this sort of picture if we plot that ratio S2 over S1 versus the S1 variable. We should get a picture like this. So at LBL, we have a setup with a neutron source, and we sandwich it between a lead block and a sodium iodide detector, which is used to tag 4.4 MeV gammas coincident with a large number of the neutrons that essentially say, okay, a neutron is out there. We look for events like this, single Gaussian-like pulses, and when we cut down to those sorts of events, we get this sort of picture. We can identify higher energy gammas here, the xenon X-rays here, and this darker band, which we believe to be the nuclear recoils. Now, I didn't say much between here and here, or between here and here, but it took a long time between when we first set this up to where we actually got this plot. But so in order to test that these are actually nuclear recoils, we've placed a gamma source here, sodium-22, so we should get two coincident 511 keV gamma rays. We use a similar tagging strategy, and so we're looking now at gamma events. And so we look at the gamma events versus the neutron events, and we've managed to get enough statistics that we're confident that we see this nuclear recoil band here and not here. So the next step now is to actually quantify what the energies of these recoils are and determine so based on the spectrum of those recoils, what this axis actually is in nuclear recoil energy as they've done in xenon. That's the quantity of interest for characterizing xenon as a dark matter detector medium. So, I'm sorry, this is just the same plot labeled. And so that was kind of the research that I've been working on for the past few years, the past 4 years. And if we detect neutrinoless double beta decay, it's significant in terms of understanding the neutrino. We've shown that gaseous xenon has the energy resolution necessary and properties necessary to be competitive in a neutrinoless double beta search. And of course, the nature of dark matter is uncertain, and we hope that we can develop xenon also into a possible dark matter detector medium. So further development is on the way for that. So thank you very much to SSGF and to Krell Institute for supporting me for the past 4 years working on this, and thank you for your attention.